So, hello and a warm welcome and namaste to the third and final day of this RL workshop. It's an honor to have Prashant with us, who will be speaking on a cubic regularized policy Newton algorithm for reinforcement learning. So, maybe a quick introduction about Prashant. So, first, I'll give an informal description. See, when we are students, we always have one student among our group who always says he's ill prepared for the exam and will go on to top the exam, right? So, I think one would say that Prashant is the faculty analog of that. So a brief description of his career so far is as follows. Prashant is an associate professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Madras. Prior to this, he was a postdoctoral researcher at the Institute of Systems Research, University of Maryland, College Park from 2015 to 2017, and at Indria Lil from 2012 to 2014. He has also worked with Texas Instruments for close to 7 years, and he has received his master's and PhD from the Indian Institute of Science, that is this own place. So his PhD advisor is sitting in the front row. His research interests are reinforcement learning, simulation optimization, and multi-arm bandits. I would like to emphasize that he is a co-author of 2 books, the first of which is Stochastic Recursive Algorithms for Optimization, Simultaneous Perturbation Methods, and Risk-Sensitive Reinforcement Learning via Policy Gradient Search. Over to you, Prashant.
Okay, thanks for the kind introduction. Thanks to organizers for this opportunity, and thanks to all the students who managed to wake up and turn up here. I usually ask this question in my class: how many of you slept before midnight? On an average, only 1 or 2 hands go up. So the bulk of the class sleeps late. So I sleep late. The students sleep late, and we exchange suffering in the class. Yeah. So. Yeah, it's good to see that there are others who suffer. Maybe some people who are sleeping. Yeah, we wish them good luck. So this is some work that we recently got through our annual conference, IISc, which is one of the good conferences. This is joint work with Nishan, who may be here, is not yet here. Was my former law degree student. Akash was Professor Bhatnagar's master's student. So, just to keep things interesting, I know it's the 3rd day and it's a morning, so I mean, if all of this material is not interesting, I just want to give, tempt you with saying that there are 2 comics and a poem coming at some point, random points. One of the comic is about happiness, the other is about ChatGPT, and the poem is about how to handle ML conference submissions and rejects and things like that. Yeah. And the poem is an original, not written by me, and not written by ChatGPT. You need to add that this. One slide summary. So we come up with a new algorithm. A second order algorithm, policy gradient methods are popular. So this is a second order algorithm. And for a second order algorithm, in addition to the gradient, you need to estimate the Hessian. And to show any convergence result, you need to quantify the bias and variance. And after that, this is a term that comes up later. This is better than stationary count that you may be familiar with. We show some convergence. This is. Sorry, there is some typo here. And reinforce only converges to a porosity. And then this algorithm has to solve an optimization problem, which may not be easy. So we come with an approximate variation, use gradient descent to solve a certain subproblem, which is this cubic model. And we use only Hessian products to solve this problem. Somewhat, we're getting towards computational efficiency, but not yet there. And then we show SOSP same convergent current as this. Forget this are typos. And then we show some simulation experiments on Carpol and Mojoto. And I just want to add that at some point, after I finish presenting this work, towards the end, I give you a sneak preview about 2 of my recent results in the context of risk-sensitive reinforcement learning. So the overall outline of the talk, we'll start with it's the crash course, the fastest one, where I tell you what a finite was in MDP is. and introduce policy gradient framework. And I need some concepts from stochastic non-convex optimization. There are advances. There will be a speaker on this some point today, probably the third talk was an expert on this, and we'll take some notions from their papers. First and second order stationary point. IISc follows second order stationary point. And then what kind of guarantees we can get, how do I get to a second order stationary point? Advances there, and then we'll outline the challenges on the RL side. So I want to bring in these ideas, show convergence to a point which is better than a first order stationary point, and show why we have to take the cubic regularized Newton route and not something else. And then the theoretical results, not just asymptotic, we give bounds that hold in the finite sample regime, and then the approximate solution with guarantee. So the same guarantee, but a faster way to solve things and experiment. So this is the outline. At any point, feel free to stop and ask questions. Introduction. So this may be unnecessary by now. Everyone knows what an MDP is with the Markov property. And then you also know, by now many of you know, that we are in the reinforcement framework where you don't know the transition probabilities, you still learn, you try to choose actions or a policy to optimize some performance measure. In this case, it's the value function. And the underlying formalism is MDP. Yeah, this is all well known. So we are in the finite is an MDP setting. So the policies are stationary and randomized in the sense for a given state. This quantity says what is the probability of choosing action A in state S. So I have randomized policies in any state. I get a distribution over actions, and then if I look at a particular trajectory, imagine like this, where H is the horizon I'm looking at. It's a finite horizon MDP. Then the probability of that trajectory is this. So probability of starting a state, imagine if it's a state and can cut this out. And then taking action A0 in S0 and then going to S1. I mean, all of these things have some randomness. So policy is random and then there is a transition probability. So you can associate, for the entire trajectory, you can associate the probability of seeing that trajectory. Yeah. And now the performance measure is this, which is the discounted sum of costs for the given policy. So I'm choosing actions according to pi. I accumulate the cost with a certain discount, and I want to minimize this. And I take this expectation over all possible sample parts of trajectories. Yeah.
If AH action is taken at SH, doesn't it guarantee will go to SH plus 1?
No, it's a transition probability associated with it. It's a random probability. It's a Markovian evolution in a particular state. You take an action and with different probabilities you go to different states and they come. It's like a Markov chain but add a control component. So that's the RL101. But I can only clarify as much. If you want more, you can join IIT Madras. I'll teach you a semester long course. And give me good ratings. Yeah, don't forget it. Yeah. Anyway, policy gradient framework. One popular way of solving these problems is, you parameterize the policy. It has a parameter, and you try to search for the best parameter within this parameterized class. Simple old world features is this. The linear, kind of products here. This IISc are the features, state action features, and theta is your parameter. So this is giving a probability of choosing action A in state S, and its parameter is like this, and the features are fixed. The outside, imagine you fix the features, and you want to find which is the best data to, you want to solve this problem. And there's been a lot of interest in analyzing policy gradient algorithms of late in the last 5 years or so. Lots of papers, and this is just a representative set. There are lots of papers. Just look for policy gradients, stationary convergence, bounds, things like that. Get thousands of papers. There are hundreds of papers of this. Yeah. So just to recall, so I'm going to replace pi with theta. So it's like, a policy is identifiable with the parameter. So with theta. And this is what I want to optimize, where these actions are chosen according to a policy that's parameterized by theta. And if you want to do a policy gradient update, I'll do this iterative the incremental update where I estimate the gradient of this function. And then I wrote this. Yeah, I'm in the cost regime minimization problem, so I'm doing this. And some of the questions are like, how do I form this estimate using sample parts? And what is the bias and variance? This is not the contribution of this work. This is fairly well known in policy gradient literature. We want to get to second order, but I'll briefly tell you how to form these things. Yeah. But before that, since review what is coming next, which is like, there are two options. If you have done first course in optimization, if you looked at, all the design schemes, the first option is like, simplest one is gradient descent, and then you can go on to a Newton method. And there are pros and cons with both. Gradient descent is easy to implement, but then it converges slowly. It moves fast initially. If you have implemented this, you would have seen this. It moves fast initially. When it gets close to the optima, it becomes slow. Any SJD implementation, implementer will suffer from this observation and will try to make it work. An alternative is to do a Newton step like this. It uses curvature information at second order. So this is the estimate of the Hessian. This is your gradient estimate. We are in the stochastic world. And when I get close to the optima, this converges much faster because it's a quadratic approximation. But there's an extra computational burden in this since you have to estimate the Hessian in addition to the gradient, the inverted, naked. And there's also the problem that this sample Hessians may not be invertible, you have to do some tricks, project, and things like that. So there are some challenges here. And what is the best of both worlds? The best of both worlds is an algorithm that whenever the gradients are big, then do normal gradients, something like this. And when the gradients are small, then use something like a Newton step, yeah, which is use the negative curvature or negative eigenvalue of the Hessian and use that to descend. All this can be justified as in Taylor expansion, some of that may come. So you want to do some combination like this, an algorithm which splits and does that. And cubic regularized also Newton, which is based on cubic regularization of so and someone else in 2006, I think Polyak and Mistro. This is an algorithm that gets to this best of both worlds and also escapes saddle point. We'll get to what a saddle point is when I do the non-convex optimization model. So this is so the point is I want to do something like this in a policy gradient framework. I want to estimate Hessian and do cubic regularized policy Newton and also show that it converges to a local mean. That's really the ambition of this project that I embarked on more than a year. So in infographic, you have a policy, you simulate some number of trajectories, estimate the gradient, estimate the Hessian, and use them both, update your parameter in whatever variable. So this would be a broad schema for a second order algorithm. How you update this depends on whether you're doing normal Newton or a cubic regularized Newton or some other variation. Yeah. Just a quick intro to how to estimate gradients, and that principle will carry over to estimating this. So in case you have not seen this trick, it's known as the likelihood ratio method in some literature and score function also. Yeah.
This slide, you have to in parallel estimate the gradient and the Hessian. Do you also have to worry about the correlation between the samples that are used to estimate these things, and do you do something to break that correlation, or that is not needed?
No, I think in cubic regularization the correlation won't be a factor. Yeah. In a Newton method, maybe you have to be worried about it. In any case, probably you will double the number of trajectories. Yeah, you will double the number of trajectories. In terms of bounds, probably a factor of 2, but in a cubic, when you see the cubic regularized problem, I think you'll see that this product won't come. In the Newton step, yes, because you have a product. If you use the same stuff, then to show that this product can be replaced by the Hessian and the gradient, you need to worry about some things. But in cubic regularization, some of them manage to sidestep this. Yeah. Anyway, so likelihood of score function, lots of literature. I am not putting the references to this. look up likelihood ratio method or score function. Interesting references going back to 80s. So the idea is this: imagine simple setting where you have a random variable, where the kinds where the PMF is parameterized to beta, so something like this. And if I want to take the derivative of this, under some regularity as derivative inside, maybe we can do that. And then I can write this as like this. So what happens is this quantity, whatever this summation, I have adjusted so that it looks like the expectation of this. Okay, so this carries forward, this way carries forward. So if you don't see it here, you won't see it later. So the point is, this is an expectation of this function of the randomly. Yeah. And so if I want to estimate, so what I can do is I can replace this expectation by this. That's what we do in general. Yeah. So the likelihood ratio method is to come up with this thing, and usually in the parameter, because of parameterization, you can write this down at least in RL setting exactly. So you get samples from X and do the average. Yeah. And you can extend this. So the derivative estimator is this, or you can do a sample of this. This is one sample estimator. And then you can extend this to a Markov chain, move to a non-ID setting with some structure, Markov chain where the transition probability matrix is now parameterized. You have a theta, and you have some function. You have some function that of this, and you want to estimate this. So in this case also using the same kind of trick, I get to estimate like this. Yeah, the same kind of tricks go through even in the Markov chain setting, and that eventually leads to what is called as the okay. So this is the so you have some function of this Markov chain with parameterization denoted by theta. So what you do is get a sample path. Imagine you are like this is like an episodic setup in common RL parlance. So you keep on there's one recurrence that denoted by 0, all others are transient. Imagine the chain is such that with positive probability you hit this starting anywhere. Then you can estimate the gradient of this performance measure like this, by similarly something. Yeah. So you can replace this expectation by sample average with multiple sample paths all ending in 0. Calculate this quantity on this one. Okay. So that's the likelihood ratio method. That's a very quick introduction. You can read up more on this. So the question now is, I want to Cauchy gradient theorem is well known. I want to take to the Hessian, but before that, some assumptions. The assumptions are not going to be on the objective. The assumptions are going to be on the parameterization, which is the policy. Once you have that, then we want to show some smoothness results. And once you have the smoothness results for the objective, then you can probably invoke ideas from non-convex optimization, stochastic non-convex optimization. The simplest, easy to justify is assume all costs are bounded. This is not a problem. And then this assumption about parameterization, pi is my policy, parameterized by theta. This is common to all Cauchy gradient algorithms analysis. What is extra is this, because I'm getting to a Newton method, I need something extra. So this second order assumption on the Cauchy parameterization is in addition to a normal Cauchy gradient analysis. If you're getting to the Hessian or trying to get to a second order stationary point, escape saddle points, then an assumption like this would be necessary. Yeah. And for the Boltzmann parameterization, it's easy to show that for Boltzmann policies or Gibbs policies, it's easy to show that such an assumption is satisfied. But for other parameterization, it's entirely unclear. But for the analysis, this is what we see. Yeah. And under these assumptions, this is well known. Cauchy gradient theorem is super well known. Even Cauchy gradient algorithms would have run into this, where you have this trajectory cause, sum them up with this log pi, and hopefully you can see that this log pi is coming because of the likelihood ratio trick. And once you have this, the question is, I start with this, I differentiate this again, I get to this. If you look at this, there are two terms. I have two terms here. So you can expect two terms in the Hessian. Yeah, and this is the Hessian. Again, this is some function of the P that was written up here. And this is how, so it's like an expectation of this one. Yeah. It's an expectation of this quantity, and this expectation is our trajectory. So for a given trajectory, in principle, I can compute this entire thing. So if I want an estimate of this, then I'm going to replace this person. Yeah, or some other method. But in essence, this is the feeder for making up my Hessian estimate.
So, what is psi I and what is P?
No, this is the sum starting from H equals I.
When
You sum the trajectory cost starting from intermediate points from 0 until the end. H is capital H is the horizon. You sum the trajectory cost from different starting points, which is a time index. And then P is this where you are taking this total cost from different points, multiplying by this is the sum for all start points. And
how are the actions chosen in that?
this is for theta. So it's hard to put everything out, but the point is all the actions at any point are coming from theta. And theta is randomized, so I cannot write it as phi of something, but the distribution that's governing that is that. So these two are random variables. If I take the expectation over trajectories, then I get the gradient. This is well known. This is well known. So if you look at reinforce, all reinforce does is takes one, either whether one sample of this or a sample average, a mini batch, variations. There are very different variations of reinforce. And the point I want to make is from here to here, we get the Hessian and you'll see two terms. So everyone sees that there will be two terms because of the form of P. There are two things there. So just the product rule. So I have two terms and I have a way to estimate this. The point I want to make is with these expressions and with the assumptions that I said about policy parameterization, I want to establish smoothness so that I can bring in some ideas from stochastic non-convex options. I want to establish that my objectives, Lipschitz, gradient Lipschitz, and also Hessian Lipschitz. And to do any of that, I have to use these two expressions and also the original expression for J. So that's really where I'm looking. And we managed to do that. So this Hessian expression is there from a HCML 2019 paper. For completeness, we have it in our paper. But this part of Lipschitz Hessian is really a contribution, a minor contribution, but it's a useful contribution to show that under assumptions that I mentioned before, I get smoothness also. I get smoothness all around. Yeah, that's first order as well as second order smoothness. You want to call it. In fact, this result, usually this result leads to, the classic alternative way of writing smoothness where you replace this by a L square or something like that. So, this kind of Lipschitz Hessian leads to a cubic expression like this. Now, I want people to hopefully remember that there's a cubic expression here because the algorithm that we are going to come up with cubic regularized is based on solving a model like this. You are going to optimize this to come up with yourself. When you look at Newton methods, you don't have the cubic term, and you solve this, the best increment that you would get is the Newton step. So you get to one more step. To one more step, add this cubic term and then solve it. Yeah, that's the cubic regularization part. We'll get there, but this is where the genesis of cubic regularizations. Yeah. Any questions? Okay, so this is the first. In case this was too overwhelming. Yeah. My jokes are not contextual. It's just, random stuff. Yeah. There's a filmmaker like this from 1950s in Japan. His movies have this interleaving shots of nature. It has nothing to do with the story. I'm not going there. Humor is what I mean. Okay, some one-on-one. So the point is I've established all smoothness results. Now, in case you don't know, we want to understand the different, at least the first and second order stationary points. So this is like the menu of stationary points, at least the first two of them. First order is a normal stationary point. You must have seen this before, where the gradient vanishes. And we want to do a finite time analysis. So if I run the gradient algorithm for a fixed number of steps, I want to show that I got to a point where the gradient is small, the size of the gradient. The way to do that is to use something like this, norm of the gradient, and say that it's smaller than 6. Yeah, so this is this version, epsilon version is for finite time guarantees. This is where the algorithms will eventually converge when you do gradient descent. A second order is this, where the gradient vanishes and the descent is positive symmetric. Yeah, that's a second order stationary point. And an epsilon version is like gradient is small and the Hessian is nearly positive symmetric. Nearly. Yeah, that's a second order stationary point. I mean, the infographic from somewhere should hopefully give you an idea. So, any questions about this? No? So the question is why this way and why not positive definitions? That's something that, because if I can get to a point where I can achieve this, then I know I found a local minimum. But why not qualify that as the SOSP and why come up with a definition that I go there? The approximate version is not the problem, but why start with the definition? That's the first question that we should think about. Hopefully, I try to answer that. And the second thing is, okay, the basic thing is like in the non-convex optimization setting, when you plan, like for example, in policy gradients, you can't ensure convexity. If you're making that an assumption, there's no justification for that. You can parameterize the policies, but there's no guarantee that the value function is convex. So you are in the non-convex regime, and in the non-convex regime, if you find a first order stationary point, it could be arbitrarily bad. I mean, it's like the joke is like imagine you go to a movie thinking it's a romantic comedy, but it can turn out to be a horror movie. It's like that. So you want to converge to a local minimum, but maybe you got a local max or a saddle point, things like that. So you don't want that. Yeah.
The previous slide, is it clear that the epsilon version, when you look at the SCN should be greater than some order square root epsilon that occurs?
Yeah, we will get there. But I just want to motivate this thing first. I'll get to that slowly. Yeah. So the point is, I mean, this is just an example. It's not enough simply because a simple example where the gradient vanishes, but you still haven't got to a local minimum. I mean, if you have taken an optimization course, this is one of the conditions for local minimum, positive definiteness plus gradient vanishing. Now, if you want to iterate further, then if this is 0 and if this also vanishes, then look at the third derivative and so on. You can keep on iterating this, yeah. But the later second order stationary point, because trying to get a second order stationary point itself is quite an ordeal in terms of algorithm design. The second thing is why positive semi-definite, because it's simply hard to find a local minimum. You can look at a paper by Hanmashri Anand Kumar on this. Ask me for the reference of forward to put it here. But the point is, if all the saddle points are split, which is this condition, then if you get a second order stationary point, then you have found a local minimum. Otherwise, you can still be stuck in a bad place, something like that. Missing also vanishing. So we're going to sidestep all of this because we can't impose any condition on the J. This is saying that we have a Cauchy gradient algorithm, a variation of that. It comes to second order stationary point. If the function is well behaved, maybe you got a local minimum, otherwise you got to a scheme. And you can come up with a new algorithm which goes to third order stationary point and still have the same problem. Here again, you're not entirely sure if it's a local minimum. So that problem persists, but at least a strict saddle condition, which is common in the literature in stochastic non-convex optimization, you can escape. You can ensure that convergence to local minimum is good enough. And many the motivation for this came from ML training problems. Some of the problems where a local minimum is as good as a global minimum. Many of these problems, training problems, and so you want an algorithm that converges to a local minimum. You are done. It's not still convex, but several local minimum. All of them are good enough. The image to see it as like you have a carton of X. So that's like the image of the function that you can think of. So this is what a different way of writing it. So a second order stationary point where this square is less than epsilon, so I made the square root and also made the lambda mean. I put a minus here, so I'll give guarantees in this form. This is just another fancy way of writing, rewriting a second order stationary point. So we come up with algorithms which we get there. This is the expectation version. And with the high probability also, these conditions go. So we get there with both of these. Yeah. That's really what we get to. And this is just a recap in case you forgot what we are up to. So the point is, even in RL Pulsy gradient framework, it's not enough to get to a first order stationary point. You want to get here. And for that, we are going to use ideas. So what are the two principal or popular ideas is what there are two popular ideas to get to a second order stationary point. One of them is cubic regularization. Other thing is something else which I'm going to discuss. Yeah. Any questions? So the other method, championed by these two papers, is you take your update and add isotropy ones. Yeah, so I forgot about the update here, but add noise that is rich in all directions. Yeah. So the idea is like when does a gradient descent not converge to local maybe it got a saddle point got stuck there. So you need to push it out of that. So you add noise to the update. You add noise so that it doesn't get stuck. So that's this. And the noise has to be rich in all directions or omnidirectional. Can't be like zero in some directions and non-zero in some. So this one possible candidate is this. So this kind of an algorithm. So what you're doing here is you're taking regular gradient descent, adding noise, a part of gradient descent is what we call it. It's just the appearance forward. And that will convert to a second order stationary. The other option is cubic regularization. Now, as a poser, if I take a Pulsy gradient algorithm and try to do a further GD, which is like the Pulsy gradient update where I actually inject noise. It may work well in practice. I'm not going to deny that. But in theory, what's the challenge? Is it like a straightforward? Imagine there is a proof in these papers saying that okay, if I have an algorithm like this, if I actually inject, and if you have some smoothness results, which is like your function is first order smooth, second order smooth, third order smooth, all that, then this algorithm becomes to the second order stationary point. If I take that idea, and if I take the reinforced algorithm and make up a further variation, that where do you think theoretical is? Or intuitively, I'm not going to show any lemma, there's no argument, it's just oral. Yeah.
Is your question on convergence or something?
No, the point is in terms of proof itself, in terms of intuition itself, why is it not a straightforward thing to do? The question is, you have an algorithm, gradient descent, stochastic gradient. Okay, so reinforce is stochastic gradient, and now it may get stuck in a saddle point. There's no guarantee that it will go to a local minimum. And the classic trick in non-convex is add noise. Now, if I add that, is it straightforward to infer intuitively? No proof. Intuitively, that I will get away from those. I'll escape saddle points. Let's put it there. Is there any challenge? Yeah. The theoretical challenge. It's morning coffee is still away, but yeah, the challenge is this. See, the point is this. What is happening is, if I unfortunately forgot a bracket, I'm going to tell this multiple times. So you have the actual gradient, and then you added noise which is rich in all directions. So what happens is, imagine you go to a bad place, to the saddle point, then this noise will take it away. Now imagine this noise was not rich in all directions. Okay, then can you hope to escape from such a place? No, it has to be rich in all directions. So the point is, if I replace this by an estimate, then do you see that there are two sources of noise? Does everyone see? Because this is an estimate, which is like, I can write that as this gradient plus the estimate minus this. In reinforced, that's what is happening. I run a sample path, I estimate a discounted cost, and I make up my gradient estimates using those fancy theorems that I showed with the phi and all that. But it's an expectation. Now the point is that adds some noise, and that is a noise that you don't have control over. It's just there's an MDQ which is throwing out all of this. And And you added something else also. So there are two noise sources. And if you want to make sure that overall the algorithm escapes saddle points, then these two noise sources should cooperate like those old joint families. They should not fight with each other or cancel each other. So eventually the cumulative noise, the gradient measurement noise plus this artificially injected noise should be such that, it is somewhat rich in all directions, something like that. And to ensure that you will get a condition which will not be easy to verify. Which will not be easy to verify, you're just putting some condition on. Yeah.
One question. It's not clear why you are saying both these noises should cooperate with each other. So as long as eta k is independent of that other noise source arising due to the error in estimation, it should help you escape. Like, it's not clear why they should.
No, but there will be some conditions such that that noise plus this noise is rich. Yeah, imagine for example, this is going in some direction and the other noise is just the opposite of this. I mean, we don't have a way to. So the point is that other noise not cancelling this, even though it's independent, it's not clear. So you'll have to add some conditions so that eventually the update is like this. Eventually the update is such that you have a gradient. And there is a noise which is rich in all directions. But if it is like a sum of two factors, then there will be a condition on those two factors. One of them is control. You can choose your sigma whatever way, but the other one you don't have. So this is just a high level argument. The point I'm trying to tell is it's you have ideas from stochastic non-convex optimization. The best way would be perturbed gradient descent. You don't have to estimate second order of information. It's just super simple. Just add noise to get away from saddles. But the problem I want to say is that it's not straightforward in the RL setting because there is some noise from the MDP, from this measurement of total cost and the gradients, and there will be a condition. Now, if you want the exact condition like that, you can look at Konda Bowker's 1990 paper. Because I think an algorithm where such a condition is written. You want richness in all directions so that you escape. Otherwise, you just converge to. Otherwise, all you can guarantee for a reinforced style algorithm is stationary convergence. To escape, you'll have to do something. There are other tricks, but I'm just saying that this noise addition trick is not clear. That's all I want to point out. I'm not saying that it cannot be done, but you need to do something more than just showing smoothness and say that okay, I invoke a theorem from these papers, I get to second order decision. Okay, so now to the main algorithm. I mean, the main message is that I get to a second order stationary point with this bound number sample complexity, where epsilon is epsilon. So if you look at the classic reinforced, the sample complexity is this, but it's only first order convergence, no second order. There are two other methods in the literature in the recent past. This is Hessian Quasi gradient, an ICM 2019 paper. It has a super good sample complexity, but the convergence, it uses second order information. Same as the Hessian uses all of that, but in some kind of anticlimactic situation, it doesn't show convergence for second order system point, the convergence complete of first order one. So that's the sad part. When people in AAA 2021 did something so that you get the best, but the sample complexity is 1 by epsilon 4.5, and eventually we got the epsilon 3.5. So that's really the punchline. There's another work with 1 by epsilon 4.9. I thought it's too many rows, so I'm going to ignore that. So the point is, cubic regulation can be need to work with proven convergence. That's really the deal. And so what you do is, if you remember, this is the Newton step solution to this. Instead of this, throw in a cubic term. And this cubic term can be related to whatever you're seeing because the Hessian is smooth. I mean, let's say it's Hessian. You can optimize this. Instead of optimizing this, I'll optimize this to get my next movement. That's really the cubic regulation idea. And the point is, when I do this, I replace this with an estimate, I replace this with an estimate. So there's no product of this. So that probably answers. I have to wait till here, but yeah. So for this, I need to estimate this, I need to estimate this. But I've already given you the theorems. This is a recap or deja vu for some who have remembered all the symbols. If you remember all the symbols, you can take off 10 seconds now. So this is my estimate. I can replace all of these with sample averages, which is what I want to algorithm. So the overall solution is to simulate multiple trajectories, estimate these things, solve the cubic submodel, and that will give me the answer. So if I put the cubic term as 0, then I get the Newton's. But throwing in this has its advantages. So it's a little difficult to say that it's doing the best of both worlds here. But maybe often I'll be able to explain that. But this is doing exactly like, I mean, intuitively like what I was saying before. The gradient is, I mean, you can come up with a half and half algorithm, which is like, if the gradient is big, then do, do a normal GD step, otherwise do a Newton type step. Yeah. That converges to SOHP with that split. And cubic regularization is just a fancy way of achieving it. For you to see that, it will take some time, but it's a useful thought experiment, thought exercise. So these are the estimates. I'm not going slide with a lot of expressions, but this is like, this is a sample average. If I replace this by expectation, I get the gradient. If I replace this by expectation, I get the LCM. It has two terms because the LCM expression had two terms, so I need two terms. Yeah. And these are relatives, I'll estimate a bunch of things. So if you remember this is one sample estimate. If you want a multiple sample, this is. Okay. I think you can pour over the details of the algorithm by reading this amazing paper which will come up in your research. The main guarantee. The main guarantee is that under these parameter choices, which is like the number of episodes or trajectories to estimate the gradient is like order 1 by epsilon square, or the SN is like order 1 by epsilon, with this kind of a thing. And the number of iterations for the overall algorithm, which is like 1 by epsilon for 3 by 2. I can show that it converges to a point, which is the second order stationary point in expectation. That's the main claim. And we go ahead and also show that, something like this goes with high probability. I'm not going to repeat this equation, but removing the expectation that's in the paper. Yeah. So you can show both high probability as well as expectation. When you're in the high probability case, you replace this, put a log 1 by delta somewhere, and it will be okay. Yeah. And you'll get 1 minus beta guarantee. That's that. And the sample complexities are like this. So the overall sample complexity is like 1 by epsilon or 3.5 because I can reuse trajectories. I don't have to. So this is the main thing. 1 by epsilon or 1 by 2. It's not entirely clear what's the best sample complexity to get a SOSP point, but at least in terms of the current literature, it's an improvement. This paper that I mentioned earlier is estimated for children. It gets 1 by epsilon cube, but finds the first order point. Someone else got 1 by epsilon for 4.5, someone else got 1 by epsilon for 9. So we did better. The reviewers fell for it. That's it. Yeah, that's how the ML world is. So you have to find happiness. So one thing that nobody has complained about is how are you going to solve this? Nobody has complained about this. Yeah. It's good to raise your voice. Thanks. So the way to do it is to solve this cubic model, I can do gradient descent. And that gradient descent, you will see that is Hessian free in the sense not fully free, but you need Hessian vector products. You don't need to store the Hessian matrix. That's actually a big deal, was what my former student Nizam tells me in neural network implementations, where you can do Hessian vector products a lot easily in implementation than work with the entire Hessian. If you want to do Newton, cubic regularization also Newton, or just normal Newton also with a neural network kind of parameterization for your. So this is the cubic model. So I want to optimize this. If I want to optimize this, then I can do gradient step like this. If you see the Hessian comes as a product. So as long as I can get Hessian vector products, it's okay. That's really the implication. So the idea is that I don't solve this cubic problem exactly using a solver or whatever. I don't solve this, but instead I do a bunch of gradient steps. In practice, you can do a reasonable number of gradient steps. You know that if you do gradient descent for a function, it gets close to the optima fast, although it may not get there towards the end as fast as you like. But this is a reasonable approximation. But the point is, will this still ensure convergence to SOSP? That's something which is tricky. So the point is, if I just say that I'll rent for 100 steps, 1,000 steps, whatever number you like, there's no guarantee. So you need to be clever. And that is outsourced to Carmen and Ducci and people that Michael Jordan was there. They come up with a solver for an algorithm like this with a quadratic problem. So you have a quadratic problem, you want to solve this. They come up with an algorithm which will do a certain number of gradient steps and also something else called the Cauchy steps. Will not get into the details. I can use that as a black box for myself. I will use that and I will still ensure SOSP convergence for this approximation. So this is a useful practical, right? I'll do gradient descent for the objective that I cared about. It's a quadratic problem. But if there's a clever way of figuring out what this number of steps is, and that you'll have to look at these two papers that are mentioned, Carmen and Lucci. I mean, this is Neurals 2018. I think this is Sian Journal Images. Yeah, so these two papers have those tricks. So I don't have to reinvent anything. So take that and I'll still get to a point which is approximately good enough so that I ensure SOSP convergence. So you get the same guarantee on the exponent for 3.5 sample complexity for SOSP. That's really the end of the theory. Any questions? No? Okay. Some experiments. We did carport with linear features. The Gibbs policy or Boltzmann policy with linear features. And we compared against reinforced, and then we took some Mujoko benchmarks, humanoid and feature, and we compared against reinforced the ACR field. ACR field is a nice deal here simply because it's computationally efficient, and because of the same approach, I can take neural networks for my features, use neural networks. So we use neural networks for the features here. Whereas here, with good old linear features and Boltzmann policy, I get to a point where I'm somewhat better than reinforced. Yeah, I'm somewhat better than reinforced. That's really the deal. But now tell you some two recent. Still about 5 or 10 minutes, right? At least. I have 7 minutes. Okay, so I'm done with cubic regularized approximation. If there are any question, I can take it. The other two are totally orthogonal to this. Some two recent works that I did, I thought it's still, under review, top ML conference.
The red line is also the question.
Yeah, here we wanted to do Hessian vector products. If you see here, if you see this, you couldn't find an easy way to solve this exactly or using a solver with neural networks. So what we did was we only implemented the ACRPN, the approximate one, using gradient descent. That's the reason why on Mujoko experiments, because of a neural network feature approximation, used to only have ACRPN. Here, because it's linear, Gibbs policy, I can write down the Hessian, it's a lot easier to solve it also. Yeah. Whereas in Mujoko, it's a little complicated because of the features. And it took us some while, I don't know, my student tells me that it's very hard to implement second order algorithms with neural networks. The current implementations can give you the gradients, but for the Hessian, it's quite an ordeal. That's what Nijan told me. So it took us some time to eventually get here. Okay, the last 5 minutes. Two works. The first work, both in resistance reinforcement learning, which is something that I've been looking at for almost a decade. The first one is like, going beyond IID setting, imagine a macro cost process. A macro cost process is like, a policy evaluation kind of problem. You fix a policy, you see a macro change, you have costs, and you want to evaluate not the expectation, but some other notions, risk, and you want lower and upper bounds. The other thing is like, this is in the discounted setting, go on to the average setting, and we looked at variance, and we can do a lot more for variance than the kind of complicated risk in this book here. Two things that I'm going to briefly post, not in detail, but at least this is the problem formulation. But before that, this is the chat GPT joke. Yeah. This is the brief, yeah. Valley, I don't know, actually I asked this, I've been teaching for 7 years, I've been asking students, do you do Gilbert? And they said we don't have time. Yeah. Yeah. don't have time. Yeah, we don't have time for books. We don't buy books. We don't read them. Forget reading. Don't even buy them. Well, is my favorite character because I spent, as Gohan told, 7 years in the industry. I was near the coffee machine. Yeah. Yeah, so some of my industry former peers, if they look at me giving this talk, they'll be amazed. Look how hard it got, just like Mohan in that same spirit. Because at the office I never worked. Yeah. So the problem is this. This is the random variable that you take expectation of in a discounted entity. You fix the action from getting rid of the action. To fix the action, you get a Markov chain. You're looking at a discounted, cumulative discounted cost. This is the random variable, and it makes sense to not just look at the mean, but the variance, a quantile, a conditional value address. These are things where this is called value address. This is very popular in financial applications. Now there is a lot of work on quantile reinforcement learning also. This is the quantile. And CVAR is an expectation beyond the quantile. The alpha is what decides. So these two and then variance everybody knows. For all of this, if I want to estimate what is like the bounds that I can expect. Yeah, if I'm allowed to get multiple samples, which is like simulate, get multiple episodes so that I get samples of this. I want to estimate bar, I want to estimate CVAR or variance, half a dozen things. Yeah. And what we showed to information theoretic arguments is a lower bound that goes for 4 of them, not half a dozen, but almost there. And the bound is 1 by epsilon square, and this is the bound. This is my estimate of the risk measure. Given a sample path of length n. N is the length of the sample path, and D is the cumulative discounted cost, and theta is a function of the distribution. This is the random variable of the distribution. So we look at it. So this could be a risk measure. It could be mean, it could be a quantile, it could be a position other things. For many of these risk measures, this includes at least 3 popular risk measures. So we managed to get upper bounds and lower bounds which match at least in terms of epsilon. So the sample complexity is if I want to make this epsilon, what is the number? N. How long the sample path should be. And that's what we got. And the lower bound took us some while, but we have 2 flavors, lower bounds. First one is a deterministic cost, other is a random cost, Gaussian cost. And there's a function of epsilon in the lower bound. If you have done lower bounds, you'll see that this is a big deal in the sense, one case it's model, but in the other case it's a function of epsilon. The cost function itself can diverge as epsilon goes down to 0. In either case, both these lower bounds, for not for mean, not for complicated estimates like a quantile, which is VAR or CVAR, we're able to get this lower bounds working, and even for variance. That's the thing. And upper bounds we have to truncate, whether it's a random organism or a fixed organism. It's to your liking, but you have to truncate. You truncate it, and then using those truncated estimates like episodes and episodic cost with some truncated level, you estimate all of this, and then I can give you concentration bounds in expectation, which kind of marks. That's the high level thing. Any questions about this? About the next 2 slides? Yeah. Upper bound is this. Lower bound is like for any algorithm. It's like min max lower bound. For any algorithm, it has to suffer at least this many samples. We need a sample path which is at least that long. So no algorithm here, but the upper bound is Monte Carlo. But the point I want to make is if you look at variance or CVAR, if you want to do temporal difference learning, the starting point is a Bellman equation. But if you replace the expectation with a quantile, there's no Bellman equation. I don't think there can be a easy Bellman equation. So without a Bellman equation, you can't do it. So right now we have done Monte Carlo because in the absence of anything, Monte Carlo is the thing to start with. So we managed to get matching bounds. Like even before TD, if you look at textbooks, people talk about Monte Carlo, Burt-Sakers and Rich Sutton, but they started in Monte Carlo. So there's this thing that I can get here, but getting to you need a fixed point relation for CVAR and other things. That's complicated. That's not
One more.
Okay, then the last thing I want to say is some work with Shivada Agarwal and Jyotisha Agluri at Georgia Tech. This is in average cost setting. This is the average cost everyone knows, which is like the long run average cost. Now I can look at instead of the expectation, the variance of this one. And a reasonable assumption like finite state action, irreducibility, for every start state, this is going to be the same number, just like this is going to be the same number irrespective of the start state. And an equivalent expression which is illuminating is that, this is the variance, and that can be split into two terms where, the time correlation comes here. This is like, whatever happens from start S0 A0 to Sj Aj. How do these cost products correlate as a function of time, and that comes in. Whereas in this time there is nothing. So there is a previous work by yours truly where I just looked at this as the variance measure. I ignored this time correlation. Just look at this as the variance measure and did mean variance optimization almost a decade ago. Whereas, if you throw this in, it makes things come because of time correlation, and there will be time correlation in any non-trivial MPP. And for this, we just want to say that we came up with the TD type algorithm using this equivalent notion where, Q is the differential value function. This is like a Q function that you will see in average cost problem. And with a lot of effort, we got finite sample error points. Yeah, so that's maybe the end. Some references. After this, the spirit of the next speaker managed to get a poem, not from ChatGPT. This is a real person writing a real poem in a book which is fantastic, the Poetry Pharmacy. I had to wait 15 years to put my first poem in the slides. Yeah, people can ask questions, others can read the poem, and if you want to clap, do it. Yeah.
So maybe we have time for two quick questions. So maybe I'll ask the question.
Yes.
So in your policy Newton type work, you restricted yourself to finite horizon in some sense, right? So is there a reason you had to restrict yourself? Do the calculations don't carry over to the infinite horizon case?
No, infinite horizon, I think, can be a technical extension or even stochastic shortest path. The point is again, infinite horizon can be a technical extension, yes. But if you want to do function approximation, it may be tricky. Yeah. Even episodic tasks like stochastic shortest path can be done. You'll have to throw in some extra assumptions. Yeah, you'll have to throw in some extra assumptions like proper policy or something.
I also think that assumption may be needed for the.
No, that's anyway needed for normal policy gradient. It's not a Newton contribution. Yeah. Anyway, you need proper policy to analyze classic policy gradient algorithm. So we didn't bring in anything. The only thing that we brought extra was the second order, assumption entry a while ago. But the assumption that I wanted was this. This is the extra assumption on the policy parameters. But that I need to ensure, higher order smoothness of the objective. Policy gradients, we shall stop here. But if you want to escape other points, even with a gradient descent type algorithm, you need it. You go to perturb gradient descent, then you have something like this without the pi actual function itself. So you need that even for a gradient descent type algorithm, stochastic non-convex approach. If you want to get escape saddles.
The second one is basically the difference of the Hessians.
Yeah, difference of the Hessians, the operating norm. And just saying that this is extra. You should consider if you are happy with stationary convergence first order, you don't need this. To get saddle points, I just want to say that the parameters sacrifice this, then the objective satisfies this. That's like in particular the third one.
So the difference in Hessians doesn't imply the explanation. There are any better to look in this like that.
No, I don't think so. No,
No. Second, the Hessians in previous which one they are.
Sorry, which one?
Yes, when you go back to the previous. Maybe you are writing three conditions. That's slide also.
Yeah, that's three. No, the assumptions. Sorry.
No. Can you talk to me?
Yeah.
I'm just saying that the difference in Hessians.
This won't imply the arguments.
The second one also.
No, because it's like, if a function has smooth double dash, if a function has f double dash, that should does not imply something on f dash.
No, you are not in complex domain.
Even then, I don't think so. I think we can talk about it. I don't think so.
Okay, maybe in the interest of time, we can take other questions offline. So let's thank the speaker again, and there is some. So we would now like to welcome Professor Sridhar Mahadevan for the last talk in the series. He has kept us all intrigued with his new way of looking at machine learning and trying to build it again from scratch, in a sense. So he has promised us that he would give us, in some sense, how it could be beneficial in terms of UMAP. So hopefully we will see some of those today. Thank you. Please let's welcome him once again.
Okay, so the plan for today is to introduce this notion that was originally proposed by UNEDA on sort of an abstract integral calculus and see how it gives us insight into generative AI and I think several other things in machine learning. But I wanted to, I got, I enjoyed interacting with a large number of students over the past couple of days. And the one question I keep getting is, oh, this category theory hub is really nice, but is it useful for anything? What can I do with it? Can I get rich quick? Since we heard a lot about Boltzmann, I thought we should start with a quote from Boltzmann. Which is that there is nothing more practical than good theory. If you have good theory, good practical stuff comes out of it. And I don't think we have to stretch our minds very far to see this, right? Why do we have computers? Anybody? Why do we have computers? We have laptops. Because we have solid state circuits, we have transistors. Why do we have transistors? ECE folks. I can't be the only one to know this. How does a transistor work? Yes, and how does that work? It's all quantum physics, right? The first people who discovered Bardeen, Brattain, Shockley, and Bell Labs were quantum physicists. We have computers today because of quantum physics. Of course, it should really work like a quantum computer, but it doesn't. But the underlying principle of a transistor is quantum physics. And without quantum physics, there would be no ChatGPT, basically. So theory always leads to very profound practical consequences, but it might take some time, right? So you just got to be patient, and that's part of what I want to say. So I wanted to start with a very inspiring person, and I'm going to bring her up for two reasons. One is I think she's a good example of this theme that I talked about of mathematicians who are birds and mathematicians who are frogs. And she is, to me, the consummate bird mathematician. And I also want to bring her up because she is really the original founder of category theory, because she basically laid the foundations of what we call modern algebra. And she was the first one who said, don't just look at the algebraic structure, pay attention to the morphisms, for example, that go from a group to another group, the group homomorphisms or the morphisms between one ring to another ring. And it was her sort of championship of this insight that led several decades later to Eilenberg and Saunders MacLean developing category theory. So the person I'm talking about is Emmy Noether. How many people know Emmy Noether? Far too few people. So Emmy Noether is a giant in 20th century science. And there's a famous story. She was at the University of Göttingen 100 years ago, roughly. Women were unfortunately not treated well in academia 100 years ago. Despite the fact that she was a world-class mathematician, she could not get a teaching position. So David Hilbert, who's one of the founders of math, used to offer a class in his name, but Emmy Noether would actually end up teaching it because she couldn't teach in her name. But students discovered her because she was really so brilliant, and they would go to her for their problems, and it turns out she could earn money by giving tuition, and that's how, in effect, Emmy Noether was helped by students. So Einstein came to give a lecture at Göttingen on his general relativity, and there was a fundamental question of conservation principles. It seemed like Einstein's general relativity was violating the conservation of energy property, and this completely confused the giants of mathematics, including Felix Klein and David Hilbert. And Einstein held Emmy Noether in very high regard. And he told them, why don't you go talk to Emmy? She can sort this out. And that is exactly what she did. And she proved two of the most fundamental theorems in physics that completely changed physics. So she showed that for any conservation principle, there must be a symmetry law. And for the last 100 years, this has been like the North Pole for physics, because as physics got progressively more abstract, it became very difficult to sort of use your intuition. And so physicists time and again have gone back to Emmy Noether's symmetry principle. Her two theorems sort of guide their way into the quantum world. And, you know, these conservation principles that she came up with turned out to be absolutely foundational. So this is an example of what I would call the consummate bird mathematician who saw deeply into the structure of physics and made profound contributions. But what's amazing about her is that she not only did this, but she laid the foundations of algebra. And as this article says, without Emmy Noether, there would be a huge gap in mathematics and its understanding. Because here what she did was she showed how to understand algebraic structures, not just in terms of the structure itself, but in terms of how these structures interact with each other. And this was the foundation for category theory. So a lot of the work that Yoneda did really came about because of the foundations that Emmy Noether set up. So I think it's important to understand that looking at things from a sort of high-level perspective can often yield deep insights. And these insights can have profound consequences over, say, 100 years or more. So, so let's look at one such deep insight. And what does it tell for generative AI? And that is this notion of languages and machines, right? So 70 years ago, roughly, Noam Chomsky wrote a famous paper called Three Models of Language. I think it was in a journal called IRE, which is like Institute of Radio Engineers. It was sort of before IEEE. And what he proposed there was three models, which should be familiar to all of you who have taken a class in this. There are regular languages, which are accepted by finite state machines. There are context-free languages, which are accepted by push-down automata. And then there are context-sensitive and so on, for which you need a Turing machine. And all of these machine models are essentially finite state controllers with memory, right? And a finite state controller has no memory, and then push-down automata has a stack, and then you have a tape and so on. So this is sort of the foundation stone of computer science. And so anything that comes new has to be sort of placed in the context of this work. So if you start doing neural nets, well, we have to see how these neural nets fit into this framework, right? And so there's a very nice paper, which I highly recommend, which was published in the ICLR proceedings last year, called Neural Networks in the Chomsky Hierarchy. It's not a theoretical paper, it's more of an experimental paper. The most important conclusion of this paper is that transformers are very, very limited. Okay? So there are hundreds and hundreds of tasks in this paper where transformers perform extremely poorly. It should not be surprising because transformers are very limited in what they can do. Now, what is truly surprising is transformers in the guise of LLMs are able to do all of these things that we've all seen demos of. So clearly what this tells us is there are certain ways of solving these other problems for which we thought we needed state, but maybe we can get away with a large enough context and $1 billion of computation, basically. So that's the lesson to draw from the success of transformers. So this is a paper I was talking about. Michael Hahn, who graduated from Stanford a few years ago, wrote a very nice paper called Theoretical Limitations of Self-Attention in Neural Sequence Models. And that's a very nice paper because he showed in a elegant way that you can't compute things in transformers which may be important. For example, parity function, that should not be surprising. With a two-state finite state machine, I can do parity, right? I just keep looking at the bits coming in. And if I get an additional bit and I've seen an odd number of ones, then I flip to the next state. If I see an even number, I flip back and so on. So I just need two states in a finite state machine to do parity. And yet I cannot do that with a transformer because I cannot keep state arbitrarily. I can't do integer modular arithmetic. I can't balance arithmetic expressions. So these are called Dykes languages. And so this is very surprising because people say, oh, ChatGPT can program GitHub Copilot. You have to be very careful when you make statements like that because, for example, you cannot compile a program with ChatGPT because there's no push-down stack. So the foundations of compiler design in computer science, which came from Chomsky's work and was developed by Don Knuth in his beautiful Caltech dissertation on LR parsing, that is the foundation of computer science in the sense that you can compile millions of lines of Python code or C code or whatever extremely fast. And that's because you need the stack, and ChatGPT doesn't have a stack. So when you say ChatGPT can program, well, it's not programming, and it's basically doing code completion, which is maybe extremely useful. And clearly people who use GitHub Copilot, including people in my lab, swear by it, and I accept that, but you can't say it programs in the sense that it's got to push down the tower, right? It doesn't. So it's very useful to understand the theoretical limitations of these models by reading these papers, and I find not enough people have looked at these papers, right? So this is why computational learning theory, computability is really important because they tell you what you can do and what you can't do exactly in the same way that Emmy Noether showed that behind every conservation principle in physics, there's a symmetry law. This is exactly the same kind of result. It gives you insight into what is happening. It doesn't mean that these large language models are not useful. They're clearly extremely useful, but it also tells us that we should expect to see when we use them significant limitations, and we will not know when we hit those limitations. So, okay. So there are two ways to think of learning from data, at least two ways, probably more. One is build a generative model as a probability distribution, right? And the other is to construct some sort of geometric representation or topological representation. So this notion of ends and coends unifies these two in some very nice ways. And the sort of the big idea, which I explain in more detail in this paper of mine, is that you construct. I talked about functors. Now we're going to look at something called a bifunctor, which takes the same category as input, but acts on the category covariantly and variantly. So in other words, the first argument is C off, which means that the arrows in the category are reversed. And you can show, for example, distance functions, generalized metric spaces, follow this sort of structure. So when you take that functor, you quote unquote integrate it over all the objects in the category, and I'll explain later what that means. If you compute the end integral, you end up with probabilistic generative models. If you compute the coend integral, you end up with topological data analysis, manifold learning, and so on. To illustrate this, I'm going to walk through UMAP. And although the UMAP paper does not describe what they do as a coend, that's exactly what it is. So when you look at it in a slightly more general setting, you get some insight into what's going on. And one of the things I'm going to conjecture is that all the work that people have done in generative models is sort of in this space. Maybe we can do something like a geometric transformer model. Okay, so before I get there, because all of you were asking me, is category theory good for anything at all? I said I want to start there, and for most of you, this might be your first introduction to category theory. So category theory is a very rich field, not just in terms of the mathematics, but in its application to computer science. It has been extensively explored in computer science over many decades. And the best way to illustrate that is to start with programming. So Haskell is a language that comes completely from category theory. It's very elegant. Here's an example. This is code to do quicksort in C. And this is quicksort in Haskell. The code in Haskell is elegant. If you look at it, it sort of gives you insight into what's happening in quicksort. The code in C, well, if you're programmed in C, you kind of know you spend sort of most of your time figuring out where the bug is in some line. So the real world consequence of this is that if you care about building complex software that must work reliably, Haskell is your bet. And that's why, for example, in blockchains, Haskell is widely used. Cardano blockchain is an example, right? So Haskell is a very powerful programming language. It has very nice theoretical properties. It's a functional programming language, and it is widely used. And that's one example. So here's a concrete case where category theory is not just theory, but it leads to actual code that is used in the world every day, right? So this is the first sort of main thing I want to get across. Now we come to UMAP. So this is, I think, one of the best dimensionality reduction methods today, one of the best visualization methods today. And it was developed by, so the history behind this method is very interesting. So there was this guy at Berkeley, Lotfi Zadeh. Anybody know Lotfi Zadeh? He's well known for something he came up with called fuzzy set theory. Now, I offer, I think Mr. Zadeh is not alive anymore. Is that right? Okay, good. So you shouldn't speak ill of the dead, is what is said. But I mean, I don't want to say anything. I mean, he had enormous influence on a large community of people in the US and Japan and other places. I remember a time when we used to get fuzzy, you go to the appliance store and you get fuzzy washing machines, fuzzy refrigerators, and so on and so forth. The Japanese took the fuzzy logic. Now, what's fuzzy logic for fuzzy set theory? You take set theory and you make membership fuzzy. In other words, you say, well, an element belongs to the set, not as a binary, either it belongs or it doesn't, but with some probability, except it wasn't probability. It was some number between 0 and 1. And they came up with some sort of calculus, right? But there was no real math behind it in the sense that it wasn't clear exactly what it is you were doing. The sad part of the story is if Mr. Zadeh, who was at the ECE department at Berkeley, had walked a few hundred yards to the math department and asked a mathematician, is it possible to generalize set theory in a certain way? He would have got a much better answer. And the answer is yes, it is. It's called a topos. And one of the ways in which fuzzy logic fell short was they made membership fuzzy, but the rest of set theory was kept intact, right? For example, the notion of equality between sets, and they had other problems. There was no notion of a power set. So you couldn't do a fuzzy power set, for example. So this was sort of an ad hoc solution, which nonetheless influenced a lot of people. I think thousands of papers written in journals are there on fuzzy logic. But because the underlying theoretical foundations of this approach were so suspect, I think in sort of decades to come, fuzzy logic will be forgotten. So, but is there a better way to do fuzzy logic? Yes, it is, and it comes out of topos theory, and that is exactly what UMAP is based on, something called fuzzy simplicial sets, but it is the simplicial sets that I talked about yesterday with this extra component, which you can think of as a fuzzy component, but done the right way. Now, what is the right way? There was a Canadian mathematician named Michael Barr, who about 10 years ago took this problem up and discovered what was wrong with the way fuzzy logicians had formulated the problem and showed how to use category theory, topos theory in particular. You would get the right formulation of fuzzy sets. You would get, in fact, fuzzy power sets. You would get a much more elegant thing. Okay, so that was that story. Then Spivak, who's an applied mathematician at MIT, wrote, and I love this, a 3-page paper in Arcade, 3 pages. He called it fuzzy simplicial sets or something like that. I think metric realization of fuzzy simplicial sets. I love his abstract. I think I have this image of Spivak sitting down for lunch one day and doodling on a napkin and writing this paper and dashing it off the archive. So the paper said, here's an idea for doing metric realization of fuzzy simplicial sets. I don't know if this is right. This paper may have serious errors. That was exactly the abstract, right? Writes this paper, the references were like just an author named C. Michael Barr. Have you ever seen a reference like this? C. Michael Barr. You're supposed to figure out what the reference is. Anyway, Spivak have written up, but these three Canadian mathematicians took this paper of Spivak and they developed the ideas out and it became UMath, right? So it's a kind of interesting story how this evolved. There's a website with a detailed explanation of how this works. There's code, and I want to show you. I'm just not going to walk through all of it because it will take us far too long. I just want to show you how it builds on some of the ideas I described, and then I want to show you how it compares with other machine learning methods and an example of its application. So this is the paper, and you can see that these guys are sort of math guys, which is why they can understand some of this. And if you look at the paper, and you don't have to read this, but he starts definition one, the category delta has objects with finite order sets, which I talked about yesterday, with morphisms given by non-strictly order preserving maps. And then following the standard category definition, delta of denotes the category delta with morphisms reversed. Then he talks about definition two, a simplicial set is a functor from delta of the sets, the category of sets is contribute functor from delta. So you get the idea. This paper is talking about a machine learning method, but is written completely in the language of category theory. So to understand this paper, you have to understand the category theory. There's no way around it, right? And there are things here I haven't talked about. For example, they say by the density theorem, which I know what it is, but I'm assuming most of you don't know what it is. We can write this simplicial set as a co-limit and so on and so forth. So I just want to show that this is an example of what I think may become a bigger trend in the field, because it is possible to take category theory and actually work out a really powerful method. So here are the two main things that they do. They take a data set, they represent it as a simplicial set, and they construct a functor that maps it to what they call a pseudometric space. And they call it pseudometric space because you're allowed to have infinite distances. And then they construct a reverse functor. So it's a pair of adjoint functors. Adjoint functors means the economic adjoint functor, say F from category C to D, and then it has a right adjoint which goes in the reverse direction. And it's well known in algebraic topology that you can map simplicial sets to topological spaces. In fact, the person who first did it is John Milner. I don't know if anyone's heard of John Milner. John Milner is very famous. I always say stories, and I find when I teach machine learning, the students forget all machine learning, but they remember my stories. So John Milner was the most famous undergrad in Princeton. Why? Because he was an undergrad taking a class, and like undergrads do, he slept. So the class went on, the teacher finished lecturing, and he woke up and there was a list of problems on the board. And he said, oh my God, homework. So he copied all the problems down, went and he worked crazy for 2 weeks and he made no progress. And he said, this is the hardest assignment anyone's given me. And he went to complain to the professor. He solved one part of one problem. And he went to the professor saying, this is a ridiculous assignment. This is so hard. The list of problems on the board were unsolved problems. John Milner had just solved an unsolved problem. Of course, if he had known there were unsolved problems, he would have never tried any of it. So he solved an unsolved problem because he thought it was homework assignment. See, this is why if you don't know it's unsolved, maybe you'll try it. And so John Milner was the first one who showed how to take a simplicial set and construct its topological realization. And that is the basis behind the UMath method. Okay, so there are two functors. The one I just showed you, this is the other one, which goes in the opposite direction. There's a lot of detail about how all of this is done, which I will not go into. Here's the main UMath algorithm. It takes a data set, and it's a typical dimensionality reduction algorithm. It takes a high dimensional data set, and it constructs a low dimensional faithful representation of data. Parts of it look like a manifold learning method. If you've seen manifold learning, you basically take the data and you construct some sort of spectral embedding, for example, using the Laplacian, which is what I did 20 years ago when I did proto-value functions for reinforcement learning. So here's a very nice problem that some of you may take UMAP and see how you can do value function approximation in UMAP. As far as I know, nobody's done that. Now, there could be some interesting challenges because as we know, value function approximation is a tricky problem. And it may be that this structure gives you some sort of extra power to the value function approximation. I think it's an interesting problem. So if I was going to go back and do proto value functions, now this is where I would start. Okay, so let's look at how well it does. So this is from the paper. There's a bunch of data sets. There are standard data sets from MNIST, fashion MNIST, and so on. But just let's compare with PCA, right? PCA is a 100-year-old method. It assumes data is Gaussian, which is a terrible assumption if you're doing it in sort of high-dimensional visual data. You can see it just produces sort of a blob. It's just completely lost the structure. Whereas, you can see how UMAP does a beautiful job of separating the digits in MNIST, and it does a really good job in fashion MNIST, and PCA just blurs it. Okay. So this is a concrete example where foundational work in category theory over a long period of time ended up in a state-of-the-art machine learning algorithm. I don't believe this is a coincidence. This is exactly what I think will be the new face of machine learning in the next 20, 30 years. As more of this math comes in, as more people who know category theory get into machine learning, this is the kind of stuff you're going to see, because I think it has the potential for transforming many of the things we do. Okay, so please check out UMAP, download the code. But for reading the paper, understanding the theory, you're going to have to get into category theory in a deeper way. So has it been applied to other things? Here's an example. This is a paper, it's a very highly cited paper from Nature on what they call mammalian orgogenesis. So one of the foundational problems in biology is that we start with a single cell and we start reproducing. And then at some level, there's a tissue and then organs start forming, right? Some part of this tissue becomes a heart. Suddenly the brain appears. It's like magic. How does this process of cell division suddenly produce us? Or in this particular case, they studied rats. And it's a very interesting problem. They did a lot of analysis, and guess what? They used UMAP. So a lot of the plots they produce, they actually compare in this paper Jeff Hinton's stochastic neighborhood comparing TC with UMAP, and here's what they said. Computational efficiency of UMAP markedly accelerated the analysis of mouse embryo data. We found that UMAP finished processing the 2 million cell data set in around 3 CPU hours, whereas TC took more than 64 CPU hours. So here's one little data point showing that not only does it work well, but it is significantly faster. So, and I'm sure some of you are very good at looking at algorithms and speeding them up, and there could be sort of more accelerations that can be done on UMAP. So here's a concrete example of, I think, what you can get with the right theory. I wanted to give you another example, which is collaborative design in robotics. So imagine the following problem. I tell you, we want to build a robot, or we want to build a car, anything, any engineering structure, right? So any design problem, what do you have? You want some functionality. I want to build a robot, which means I wanted to carry some payload, I wanted to move at certain speeds, and so on and so forth. Right? For a car, maybe it has to seat 4 passengers, go 300 miles on a full tank, and so on and so forth. That's functionality. Then you need resources, right? How much money will it take to build a car or robot? What sort of battery do I need? What sort of parts do I need? These are hard engineering problems. This is a very nice paper by Andrea Sensi called The Mathematical Theory of Co-Design. And it turns out, so these kinds of optimization problems are really interesting because it's not even convex or non-convex. This is not even continuous. So this is sort of a completely discontinuous problem. And yet, using some ideas related to category theory, you can solve such problems. So these are like completely beyond the scope of any optimization method I know, because you can't rely on smoothness, you can't rely on continuity. So the notion of convex or non-convex doesn't even apply here. Right? It's much harder problem. So here's an example, right? So let's say you're implementing a robot. You want to know how much payload in grams can it carry? What are the how fast can it go in meters per second? What is the cost of building this thing? What is its mass? What is its motor speed, motor torque, and so on? And it's a nasty problem because there's sort of feedback loops. If you say you want to go faster, you need to put a bigger motor. If you put a bigger motor, you increase the weight of this, and that's going to slow it down. So these sort of positive, negative feedback loops that make things really hard. You may have sort of a canonical set of building blocks for the chassis, the motor. It's like a parts catalog where you can go. You can imagine the same thing if you're building a PC. How many people have built a PC? Nobody has built a PC. Really? Assembled, that's good enough. I built a bunch of GPU machines when I got excited by this stuff on Atari video games. I think I moved to Adobe, I left all of them in UMass, and probably at this point they're all thrown out. I don't think Phil Thomas is in use for that, but it's great because you start with a bunch of parts, you got some, how much money you're going to spend, you put it all together, you turn it on, nothing happens, of course, because you screw something up, you have to go in and rip it apart and see what's wrong. So any engineering problem, we have to put things together. These are hard problems. And how do you use category theory? Now, this is a very nice book I want to recommend to you. This is based on a course that started at MIT, originally by Fong and Spielberg. And it's all about how to reason over compositional structures, right? So I have these building blocks, and they each have some functionality, and there's feedback, and all kinds of, there are lots of nice engineering examples here, electric circuits, design problems, databases. So if you take standard databases, right, relational databases, corporate data all across the world is stored in relational databases. Relational databases define categories. So you can bring category theory to relational databases, and all the standard operations you do, like joins, merges, all those things can be explained in terms of category. So what they do in this book is to show that this problem that Andrea Sensi does is nicely modeled by something called profunctors, which I don't have time to explain to you, but you see the same pattern happening where you have this bifunctor that depends contravariantly on one argument and covariantly on another argument. And the reason this happens is when you take a design problem, you have resources and you have functionality. And the problem, the feasibility of a design depends contravariantly on one and covariantly on another one, which is why it's a nice example of a profunctor. So this is another nice way to think about, why, category theory is helpful.
Question.
Yes.
The course and the notes that you showed, is there a good introduction to category?
Yeah, that's what it's supposed to be for. It's kind of a little quirky because they start with things like Galois extension. In other words, in a way, it's nice because they don't start with category theory right away. They start with pre-orders. And so, for example, in this particular problem, we have resources and you have functionalities. Both of those you can think of as like partially ordered sets or pre-ordered. And so the book starts with pre-orders, and then sort of doing adjoint functors. They basically do what's called Galois extensions, which is you map one pre-order to another pre-order, right? And then they build from there, and then it's actually very nice for reinforcement learning people because they spend a lot of time modeling costs in an enriched category. So they slowly build up, and actual category theory only is some sort of somewhere in the middle of the book. So in that sense, it's a nice, and they did it specifically for teaching MIT. I don't know if undergrads took this course, probably, for MIT students, so sort of engineering learning. So. Okay, another example is there's this Python package called DiscoPy, which lets you compute with string diagrams. And there are all kinds of cool things people are doing in this space that I don't have time to talk about, which is, so there's a very fast growing area from quantum machine learning, because We are rapidly moving towards a future where quantum computing might happen. We already have prototypical quantum computers that are being sold. You can buy quantum computers now. And so the question is, how do you use deep learning on a quantum computer? There's some clever algorithms. People like Seth Lloyd, for example, at MIT has come with a very, very fast way of doing AX equal to B linear system solving, exponentially faster than classical computers. But the way you program quantum computers is completely different. It's completely different. It's like you solve some sort of a diffusion process to solve the linear system. So it's sort of, I don't know, it's kind of cool. But the advantage of category theory is that you can extract from all of that and say you're computing a certain kind of category. And it turns out you can do something like backprop, but by differentiating diagrams. It's really interesting. Okay. Ben, here's this very nice thesis from Oxford that just came out, Trinity College 2022, on category theory for quantum natural language processing. So you can use DiscoPy to basically write down statements in natural language, gets converted to string diagrams, and you can run on a quantum computer. That's been done. Now, is this going to challenge ChatGPT? No. Okay. This is not anywhere close to ChatGPT, but this is the beginnings of what might lead to a better ChatGPT in the future. Who knows? So the strange thing that happens here, if you take a sentence like "she who hates Bob," they construct the meaning of the sentence is in quantum entanglement. And Bob Koch, who's one of these pioneers of this category theoretic way of looking at quantum computing, is a big believer in this notion that compositional semantics in natural language is very well modeled category theory. And there's these things called Lambert grammars, which have been known for decades, that actually came out of category theory. There's a book on natural language models using category theory. So a lot of work actually that people have done in the NLP space using category theory. Okay. I sort of went through this long thing because I wanted to make sure that you understand the space is rich. There's plenty of space here to be like a frog or a bird, depending on what you want to do. And you shouldn't sort of think that this is only theory. There's actually very, very good practical things that you can do. All right. So in the last, how much time do I have? 15 minutes, perfect. Okay, in the last 15 minutes, I'm going to finally talk about ends and coends. And the reason I pushed this to the end is this is probably the most difficult. You probably think, oh boy, the rest of the stuff is easy. This is probably the most difficult part of what I want to say. I'm not going to explain it very well because I'm understanding it myself. And I think the more I try to explain it, maybe the more I understand it. Everybody who teaches figures this out. But I want to give you the high level idea. In particular, I want to show you why UMAP is basically computing the coin. Okay, so we talked about natural transformations. Remember, we have functors that map one category to another, right? And then the functors interact through natural transformations that give us the Brunetta lemma. Right? So what's the big difference here? The big difference is we have bifunctors. Bifunctors take two objects, right? So from the same category, except for this one, they're going to act contravariantly, to the next one, they're going to act covariantly, and then map it to some other category D. So now, let's say I have two bifunctors F and G. I'm going to compare them using a dinatural transformation, and it looks kind of like this. So let's say I start with F of C prime C. C prime is just two objects in the category. F of C prime C must be some object in category D, right? Doesn't matter what it is. So I can go, if I go this way with the morphism F, now morphism F actually maps C to C prime, but because it is contravariant, the arrow gets flipped. So I go from FC prime C to FCC. Okay. Here in the second argument, it works covariantly. So I go from FC prime C to FC prime C prime. So I go from C to C prime because that's the morphism. This just shows you that in one direction I go contravariantly, so the arrow gets flipped. The other direction I go covariantly. I can do the same thing with G, which is the other bifunctor. And then the gap is exactly what I fill with a dinatural transformation. It's short form for diagonal natural transformation. Okay. The reason it's called diagonal natural is because you're on the diagonal. Here, CC, FCC, GCC, and then you have FC prime, C prime, DC prime, C prime. Okay. So this is the basic structure. So we have these diagonal natural transformations between bifunctors, and we're going to construct a so-called category of wedges, where every wedge is sort of this diagonal natural transformation between two bifunctors, and then we ask what is the initial object in this category of wedges and what is the final object, right? So we can define wedges, we can define co-wedges, and from here we get ends and co-ends. Right? So this is sort of a very high-level explanation of what these things are. And you look at this and say, how in the blazes does probability come out of this? But this is what happens, right? It's just like physics where you say, well, there are bosons and fermions, but they produce everything. There's a big gap between the theory and what actually happens, and this is one of those cases. Okay, so let's just assume we understand that at some high level. What does it mean to geometrically realize a simplicial set? This was Milner's contribution many decades ago. So we're given a simplicial set, which you can think of as a data set we want. We want to produce a topological construction, topological representation of the simplicial set, which is indicated here by this pair of vertical lines as the topological realization of a simplicial set, which you can write in a very condensed notation as this is basically union, but in category 3, this is for the coproduct. So we're going to take a coproduct, and delta n, remember, is the simplicial category that I defined, where for every n you get objects that interact with higher and higher dimensions. So 0 means the objects are not interacting, 1 means they interact with each other pairwise, 2 means they are in 2 simplices, 3 simplices, and so on and so forth. So that's a simplicial category. That is the contravariant functor that maps the simplicial category to the set X. You take the product of that modulo some equivalence relation, and it's that equivalence relation that defines the base and degeneracy operators. Now, it's a very standard way of representing n simplices by basically taking n plus 1 real numbers that add up to 1, right? So you take n plus 1 real numbers. It's a standard sort of way of representing topological simplices. So now these spaces, what is the equivalence relation? So here is sort of going by defined for the simplicial category these primitive injections and surjections. This is what they are. So the primitive injection is if I take an n simplex and I want to map it to an n plus 1 simplex, I simply nuke out the ith argument, right? So I make that 0. So I take these numbers and then I add an extra 0. So I embed the n into the n plus 1. And when I go from the n to the n minus 1, I just add the 2 successive elements. So this is a very simple way of implementing phase and degeneracy operators for a topological n simplex. And what Milner did was define this equivalence relation that gives you the quotient space. So this is very detailed construction that Milner did in a paper. I think it was published in the Proceedings of the National Academy of Sciences in the 1950s or something. But the nice thing is it's a co-n. That's all it matters. You can show, and this is Saunders' claim shows this in his book on category theory, that this topological embedding is nothing but a co-n or a bifunctor that is written in this form. So essentially, that's sort of the high-level way to think of what UMAP is doing. It's constructing co-ns from data. So this is what I said when I said, let us think of machine learning as not learning functors as functions, but functors, right? So this is essentially this is what UMAP is doing. So this leads to this very crazy idea that I talked about in my paper. Can we construct sort of a geometric transformer, right? So remember that I showed you in the first, yesterday I think I showed you, that we can take transformers and basically view them as morphisms in a category, and then we can construct n-length morphisms that gives us a simplistic set. Now, instead of taking that and building the standard probabilistic representations or probabilistic generative model for transformer, we can instead do a sort of UMAP-like construction and compute the coend which sort of embeds transformers in a topological space and do something with this. So why should this be anything that we should do? Well, the nice thing is there's this thing called a Kahn complex. And mathematicians love Kahn complexes because they're very nice. They have all the right properties. And so the conjecture is that this is something that really will help us, right? So why should Kahn complexes be helpful? So I wanted to give you one concrete example. So you've all seen all these great, wonderful demos, Adobe Firefly, Stable Diffusion, all of these. The reason they work well is, and I think nobody has pointed this out, they are actually they are in a Kahn complex. So what does that mean? So remember the way, this is supposed to be an actual demo here, but I think the PDF won't capture that. This is from, so Song is one of the leaders in this field. He did a beautiful thesis at Stanford on building generative models in a new way using these gradient scores. He spent, I think, a year or two at OpenAI, and he just started a new faculty position at Caltech from this spring. So remember, we start with an image, we have a data set of images, and then we're going to progressively add noise, right? So remember from yesterday's lecture that any probabilistic process like this is a coalgebra. So essentially, I started with a collection of nice clean images. I started adding Gaussian noise, right? Every step, I add a little bit more noise, a little bit more noise, a little bit. This is a stochastic process, right? Now, the whole idea these stable diffusion methods work is that there's a final coalgebra. What is that final coalgebra? Pure noise. So the only way this thing will work is you must have a final coalgebra where you terminate. And the way they do it in practice is that they construct these noise sequences using Gaussian so that there's theory that basically guarantees that you will converge. It will not go on forever. But that's not the only thing. So the first requirement is when you run stable diffusion process, you converge to a fixed point, which is a final coalgebra. Right? So basically adding more, if an image is pure noise, it's like the old TVs that we used to have, analog TVs, if you turn them on, you just get, there's no station broadcasting, you just get pure noise. And if you add noise to a pure noise signal, you get nothing, you get the same thing back. Right? So it's a final coalgebra. But that's not the cool thing. The cool thing is, how does this work? What's the next step you have to do? I'm sure some of you guys know stable diffusion. Yes, you have to go back, right? So you start with your data set. This is how they build generative models. It's a cool idea, right? You start with your data set of whatever data you have. In this case, it's images. You start adding noise. You go noise, and then now you have pure noise. Then you go back, and voila, you start cleaning. Right? So new images. You can do all these cool things. Like you start. My favorite example is I take Adobe Firefly and I say, dog sitting on Mars eating a pizza, and you get an image of a dog sitting on Mars eating a pizza. I mean, here's another example where cool math actually produces something interesting. So what are these Kahn complexes I'm talking about? Every morphism is invertible in the Kahn complex. That's why mathematicians like Kahn complexes. So here, remember, when you use stable diffusion, one of the tricks they discovered was that you run the diffusion process till it converges, and then you invert the process. So every step is invertible. And this is a major trick that they discovered. And I think there's, as the phrase goes, there's method in this madness, right? I think this is important. The fact that you are in a Kahn complex is important. The problem gets much easier to solve. Now, that's not to say this is easy. It's actually extremely expensive. And one of the things that everybody's trying to figure out here is how can we do stable diffusion in a more inexpensive way? There are lots of clever ideas being tossed around. We can do it now, but it costs a lot of money. So for Adobe to run Firefly, it's a lot of money that's being spent. And for example, OpenAI to do the solar demo, I have no idea how much it costs them. I imagine it costs them a lot of money. So we can do this, but it's very expensive. So maybe the next generation of advances might come from sort of bringing in some more powerful mathematical. Okay, so let me stop there. Hopefully I gave you some sort of sketchy, hand-wavy, high-level idea of why category theory might be helpful in generative AI. As you can guess, it's primarily a theoretical exercise where you want to sort of say, can we start with this blank slate? Can we think of new ways of doing backpropagation, new ways of doing machine learning? How to implement Gaia? Well, I'm handing the problem over to you. All of you are really smart at coding. Maybe one of you can do this. Maybe somebody else will. But part of this is an exercise for me to, develop the books that I'm writing, and so check my UMass webpage. Every once in a while I might do an update if I get some clever new idea for doing. So let me stop there. Thank you so much, and I again want to thank the organizers for giving me this.
Thank you, Professor Sridhar, for this very wonderful talk and giving us a bird's eye view of how we could design the future of machine learning. So if there are any questions, this would be a good time to ask. Okay, if not, maybe I'll ask a question. So you gave us this very insightful thing about UMAP doing better than PCA. So is there a way to understand, maybe at a layman's level, why is it able to do better? Or is it that, from category theory perspective, it is doing something like maybe the PCA approach can also be understood from a category theory perspective, and perhaps one would be able to see that UMAP is doing things much more differently than UMAP, and much more differently than PCA, and hence it is able to outperform it. And would it always outperform?
Yeah, so actually, if you go to the web page, they do a lot of nice comparisons. So there's one great advantage of PCA, which should not be discounted. A lot more people understand PCA than UMAP. So in fact, Jayakumar was telling me that, hopefully I'm not divulging any confidences of his, that he was trying to get more sophisticated method for his project, and the person said, no, I like PCA, we're doing PCA. So you run into this where people know something they like. It's like economists always use least squares regression. Why? Because they know least squares regression. They understand it. If you go to them with UMAP, they'll say, what is this? No, we don't want this. So there is that, so familiarity, I think, is an important thing. So one reason PCA works really poorly, and I think UMAP is not the first method. PCA is oblivious to the geometry of the space. So I think a fundamental assumption that, in fact, everybody who does deep learning believes, and I know all the deep learning folks, like for example, Bengio in the early tutorials used to always talk about deep learning as basically extracting the manifold of the data, right? So we know that the fact that we can learn from 3D visual experience so quickly means that the intrinsic dimensionality of the data must be much lower. It's not the dimensionality is not the number of pixels in the space, right? If that was the case, we would be really hard pressed to learn. It's a much lower dimensional problem. Yesterday we were having dinner with some colleagues in Adobe, and we were talking about learning to drive, and people learn to drive in a couple of 100 hours. If you think about that, that's a formidably hard task. And I think it's because there's lots of structure that makes us learn well. And UMAP just exploits more of the structure than PCA. PCA assumes the data is Gaussian. It's a very simple assumption. PCA is a very elegant method, right? It's a method that we teach because it's easy to teach. UMAP, as you can see, is not so easy. It's much harder. So that said, I think there's some interesting comparisons between UMAP and other methods that I personally use. For example, in my paper on proto-value functions, I use Laplacian eigenmaps. And there are interesting relationships between the way The graph construction is done with UMAP. I think so. There's a lot to explore here. So let me say that. I think this is as we get more familiar with this class of methods. PC has been around 100 years, so we really understand it well. UMAP has been around 3-4 years. It's a long way to go to understand this space. That's why I think it's exciting new territory for machine learning, because here is sort of a vast new area that we can explore and try to understand what the scope of these methods is, particularly for reinforcement learning, which, as we all know, is a really challenging problem when you bring in value function approximation, right? We've already seen some talk about how difficult it is to combine value function approximation and reinforcement learning. And the open question, I think, is, do these fancier category theoretic methods give you a better handle on some of these problems? I think is a question for future research. Yeah.
Okay. On that note, let's, okay, please go ahead.
Question on similar line. So so UMAP seems to be constructed in graph, right? And if you have very large problems, generally it will be harder to scale. Whereas like techniques like auto encoder or encoder, they can just take back or return this problem. So I wonder, like, if there have been any comparison between VAs and
Yeah, I don't know if there has been, but you're right. So methods that generally work, like UMAP, I mean, clearly, for example, if you look Laplacian eigenmaps, it's in a sense like a kernel method. In fact, people like Vikas Sandwani, who worked with one of the founders of manifold learning, Partha Niyogi, who sadly died. They sort of looked at it as manifold regularization, and they looked at it definitely in the spirit of kernel methods. So you're right. So kernel methods have this problem that you basically have this issue of processing all the data. There's been lots of tricks on sort of subsampling and doing clever things with that. Some of those could be done with UMAP, I imagine. The comparisons on the web page are very revealing, because they go to larger and larger data sets. And of course, the fastest method they have is PCA, which is kind of interesting, because you wouldn't think computing eigenvectors is easy, but we just have 100 years of experience in computing eigenvectors on large matrices. We know how to do it really fast. There are lots of clever tricks. And I think the fact that UMAP is holding its speed to PCA leads me to believe that there's substantial room for improvement of UMAP. The other thing is, as I mentioned with the proto value functions work, is you start with something like this, and all the smart guys in DeepMind and all the other labs say, hey, there's a deep learning version of this. So I wouldn't be surprised if somebody has already published a paper called Deep UMAP or something like that, right? It's coming. There are papers that sort of have, as you know, they put deep on everything, right? Deep CCA, deep PCA, deep SVD, and so on. So Deep UMAP is coming. It's future attractions.
It's a general question. What's this? Today is one of the founders of this category theory, only noted. So I was just thinking, you have some idea, comments about whether person who later on become a mob, Alex, general comments.
You mean Grothendieck?
Oh, Grothendieck,
So Grothendieck, I didn't mention Grothendieck. In fact, Grothendieck was also considered one of the most influential mathematicians of the 20th century. He did a lot of pioneering work in category theory. One of his most famous contributions was looking at mathematics as if it's activity going on in a space, right? So he said, it's somewhat similar to Emmy Noether. He said, think of not the space, but functions acting on the space, right? And analyze spaces in terms of functions acting on them, which is sort of similar to this notion of looking at objects interacting in a structure. And so a lot of the ideas that Grothendieck introduced, some really elegant ones. For example, if you read Spivak's original 3-page paper, he says, we assume it's a Grothendieck topology, the line 4 of the paper or something like that. And there's a very elegant way of taking topology and writing it out for categories. For any arbitrary category, you can define a Grothendieck topology, and you get something called a site. And what you do is, in topology, you have open sets, and there's a condition on these open sets. So instead of open sets and containment relation, you define the topology in terms of the morphisms. And the morphisms have to compose in just the right way so that you get a topology. And it turns out standard topology then becomes a special case of that. And you can develop this fully. And for example, Saunders McLean has a very nice book on sheaves, which is very elegant way of sort of unifying a large body of mathematics from algebra, analysis, geometry, logic. All of it comes together in a purpose. It's called Sheaves, the geometry. I forget the title of the book, but it's Sheaves Unifying Geometry and Logic or something, and geometry analysis. Anyway, First Introduction to Topos Theory. That's the book. It's a beautiful book. And a lot of that came from the work of Grothendieck. I'll tell you one anecdote about Grothendieck, and then we can break for coffee. He was a highly influential mathematician, and he was also a very committed pacifist. He was invited on numerous occasions to lecture in the US. And at the time, I think the US was engaged in one of these Vietnam War military escapades, and Grothendieck just hated that the US was doing any of this. So in the visa interview, apparently the question was that something about the US Constitution. I think he said something that offended the visa officer. His visa was declined. He was not allowed to travel to the US. And then Harvard sort of stepped in and they brought some powerful forces there. And finally, Grothendieck did come to Harvard to give some lectures. That's one. I just got this interesting biography of Grothendieck that I'm reading. The other thing he was asked is, why is he so successful? And he has a very interesting answer. He said, because nobody before me has stooped so low. It's a very interesting answer. He said, I humbled myself in a way nobody before me did. And so I came up with solutions that perhaps escaped the others. And so it's a good motto, I think. Stoop low and maybe you get some insights.
Okay, so in the interest of time, maybe we can, have other questions later on. So on that note, let's thank Professor Sridhar Mahadevan once again.